Yeah, this.
Julian's we can test. We're almost at time. We're at
Okay.
time.
Julius, can we do a quick microphone test?
Hello, can you hear me?
Yep.
Very
Okay.
well, and we can see you as well.
Good.
All right. I think we should get going.
Yeah.
All right. Good day. Welcome to the joint session of Babel, Roll, and Manet on multicast routing. Next chart, please. You've probably all seen this, but just to highlight the note well again, and so you agree to follow the IETF processes and policies, and you're aware of the patent policy, and you, as a participant, you agree to work respectfully with others, and please if you have any questions or concerns about this, you can take that up. All right, next chart. So the meeting tips, everybody here should know how to sign in and track the attendance, and remote people as well. Make sure your audio and video is off unless you are speaking. And if you're a speaker, a headset is recommended, but we did the audio test with some people that didn't have that, so you're okay. Next one. Just some pointers to the agenda and any other information that you may need. Go on to the next chart. The resources for this session have all been uploaded, the usual places. And if you would, we could use some help with the note-taking when people are speaking, if you could do that. Next. All right, I'm going to pass this over to Ronald, who's going to talk about the agenda part here.
Hello. Yeah, we have a joint session with as topic multicast, and I'll give a short introduction, and then we go into a number of presentations. After that, we have some time for discussion, and we try to reach some form of a conclusion after that and see if there needs to be any follow-up activity to this and what form that may take. So after the presentations are done, you're all invited to voice opinions, point out deficiencies, whatever you want to do. And then we wrap up the multicast part of this session. And as by way of dessert, we have a presentation from Julius Grobacek on exciting new features in the Babel routing protocol. And that's the program for today.
Just ask for anybody, any bashing, any questions.
Yes, is there anybody who wants to bash the agenda? Going once, going twice, then we stick with the current agenda. The idea for this session was born in a conversation that Donald Eastlake had with the routing ADs, and I suspect with Alvaro in particular, because he also hinted at this after the Manet session at IETF114, and I think it's a good idea. The routing ADs have seen that multicast was discussed in various forms in all three of the working groups, but that not much progress was made. Now, whether all of you agree with that, I think it's true for MANET, but I cannot judge for the other groups. But that's also something that can come up in the discussion. Today's presentations given by participants in all of the three working groups should make clear what the challenges are, why this is not multicast as we know it in the maybe in the wired network, and what can be done about it, and if there's anything that the three groups have in common that they can work on. And then we see where we go from there. We come to that later. So can you share the other?
I think you got the control.
So first up is my own presentation. Can you do it? Okay. Yeah. But I want to stand over there.
Yeah, I'll do the right there.
Okay, good. Don't let it go to sleep.
Yeah.
Next slide.
Just got to find your page down button, that's all. Oh, okay, I got it there.
So the last time that MANET working group was recharted was in 2016.
Could you move the mic up a bit?
I'll hold it in my hand. Is that better? And then we ended up with a work item in the charter that says that we were going to continue to look at simplified multicast forwarding, which is an experimental RFC 6621. And as part of that work, we would produce a well-defined forwarding information base for multicast. And some background on how that would look like is given in a presentation that is lined out in a presentation that Justin Dean, at the time the chair of the MANET working group, gave at IETF 96. I invite you to go have a look at the slides. It's a very good presentation. But to be honest, nothing much happened since. Next slide, please. Because MANET in the subsequent years was mostly concentrating on the DLAP protocol. Lots of work happened with DLAP, but the multicast work item got neglected a bit. So even before that rechartering, there was activity. Of course, 6621 was produced in 2012. It's not really a full protocol description. It basically describes mechanisms for duplicate packet detection. Why that is needed, we will see later. It also has three different so-called relay set selection algorithms, or relay set reduction algorithms, if you want, which are described in appendices. And these make use of information that's already available from a Unicast routing protocol, MANET routing protocol, to reduce the number of nodes that are retransmitting packets. There was also some other work that has been abandoned. The on-demand multicast routing protocol. And there was work done by Brian Adamson from Naval Research Lab on elastic multicast routing. And this was a protocol that tried to have multicast group membership awareness in the routers at certain points in the network, in mobile ad hoc networks that were somewhat more stable, where there was not that much topology change. And there it could be more effective to use that. This was presented only once during IETF 88 in Vancouver. I know that NRL continued working on this, but yeah, maybe they will at some point bring it back to the IETF. Next slide, please. So what makes multicast in MANETs particularly challenging? The links can be non-transitive. So if B hears A and C hears B, there's no guarantee that that C can also receive from node A. Nodes often have only one radio interface, and they're relaying to get from A to C, for instance. And then they're using the same interface over which the packet was received to send it out again. This has some implications for some existing multicast protocols or mechanisms that do not allow to have the incoming interface in the outgoing interface list, or that try to do a reverse path forwarding check based on interface. And then there's, of course, the node mobility that leads to frequent topology changes. And it's thought that maintaining group membership on all the intermediate nodes causes too much churn because it has to be updated all the time. And hence, smart flooding approaches are used. So this is, for me, an important slide because it shows the most general link model. We have a host where transport layer and application layer protocols are running. We have a router, and we have a radio as separate entities, possibly connected by Ethernet. Of course, you can collapse this. Of course, you can have a single laptop running your routing protocol in software and using Wi-Fi as your radio. But this is the most general model, and this should be supported by our solutions. And you can see here the node in the middle relays, node B. And if it does that for a packet that started its life somewhere in node A, node A is also going to hear the retransmission again. Next slide, please. Another assumption is that we are working with radio links that are limited in capacity to the point that you can safely run your Unicast and Multicast MANET routing protocols in software. You don't need big hardware. That's the assumption. The links are the bottleneck, not the processor. And that's also, as an aside, in the DLab work that we've been doing and that Lou, for instance, has been working on, the assumption for flow controllers that the modem or the radio needs to flow control the router and not the other way around. Next slide, please.
We have a question in the queue. Do you have time to take it?
Yes.
Or? Okay.
Go ahead, Julius.
So I caution us to be careful with this assumption. In particular, all of the solutions that are going to be presented today push all packets through user space on a lot of hardware that's going to be prohibitive, even with moderate speed links. So I'd like us to be a little bit cautious with the assumption that we have plenty of CPU.
Okay, thank you for that. My radios may be slower than your radios. But So a question that has come up a couple of times: do we actually need multi-hop multicast at the IP layer? And in some of the previous MANET sessions at previous IETFs, particularly Rick Taylor has commented on this. There are solutions out there, and one is going to be presented today by Donald, that take care of multicast below the IP layer, and then make it seem to the IP layer whether that is just talking to a well-connected, well-behaved single link, and everything is one hop away and reachable, and what happens underwater, so to speak, is not visible to the IP layer. There's another technique, synchronized collaborative broadcast, roughly equivalent to something called Barrage Relay, but that's a trademark of a company called Trellisware. And that's true, of course. But what if you have an IP overlay over heterogeneous radio technology? Or what if you want to federate MANET networks that use different technologies? Next slide, please. Well, then you get into things like this. Here, the nodes A and E both have two radios. So they have one leg in one of the radio technologies and another leg in the other radio technologies. And you can see that this can lead to interesting forwarding complications where things go looping around. And again, a solution should be able to deal with this. Next slide, please. The presentation that Justin Dean gave at IETF 96, which I referred to earlier, listed a number of shortcomings of the simplified multicast forwarding, which is an experimental RFC, but the only thing that we really have in the MANET working group. Implementations are often done in user space, which can lead to poor performance. For instance, the Linux kernel doesn't really support multicast forwarding and over the same interface and all sorts of this, but that's really Henning's presentation that's coming next, that's going into that. Packets are disseminated to the entire MANET. There's no knowledge of group membership because that's considered too much churn. The relay set selection algorithms, and this goes back to the previous slide, do not support multiple interfaces well. And it's same is true for the duplicate packet detection. In ASMF, and I had to look in the code to see how it works, but I think it is per interface. There are also some circumstances where it does not work very well if you have multiple interfaces. Recently, Brian and Adamson posted on the MANET mailing list about the advances that they have been making. They sort of stepped away from the IETF and the MANET working group, but they have been continuing their work. Their NRL SMF implementation is on GitHub in the US Naval Laboratory repository on GitHub. So you can find the code there. Documentation might be lagging a bit behind. However, this has been outside the visibility of the MANET working group for some time. And what's that?
What does SMF stand for?
Simplified multicast forwarding. Next slide, please. And that's it. Any questions at this point?
We have a person in the queue. Sorry.
Yeah, Tahui or Jeffrey from Juniper.
Okay.
Sandy is going to present beer in backbone networks later. Looking at the properties of Manet you talked about, it seems that beer would be a good fit for this as well, especially when you talk about multicast IP layer over heterogeneous radio types.
Okay, thank you. This is something that during this week, David Lamparter and myself have been talking about a lot. I hope that during the discussion, David will come up to the microphone and give his opinion. But thanks, yeah, it's something that I personally don't know enough about at the moment. I'm trying to wrap my head around beer. But others have looked at it and seem to think that it might be a solution. So we need to do some work at least there. Thank you.
Okay.
Thanks for your attention. Oh, Henning. Henning, you're next. Trying to find your slides.
Yeah.
That's talking about. Yeah.
Okay, I hope everybody can hear me.
We can.
It's not something we talk about a lot in the IETF, but we are talking about protocols, the control plane, but one of the problems of IP multicast is always the data plane. It has always been, and I think this is the reason why we don't have that much work for multicast. So next slide. So I will be talking only about IP multicast routing on Linux. I don't know enough about BSD and especially about Windows. So this is Linux only at the moment. Next. What we have been doing over the years. Yeah, we have been doing multicast forwarding in user space. Next. Raw sockets. Everybody loves raw sockets. At least everybody uses raw sockets. As I think I know 3 SMF implementations. All of them are using to some kind raw socket. Next. The good thing is it works. You can do multicast forwarding with raw sockets, but it doesn't play nice with the other complicated stuff of the Linux networking code. Some raw sockets don't like firewalls and ignore them. Some raw sockets have trouble with policy routing. So if you do multi-topology routing or if you plan to do some containers, make sure to test that raw sockets don't mess up your settings. So yes, we have a solution. So next one, TAN-TAP interface. That's always, if someone says raw sockets, I normally say use TAN-TAP. Next. The advantage is it's a real interface. It's easy to integrate. The disadvantage is how to get the traffic into the TAN-TAP interface. So we're talking again about how to do some multicast forwarding, which makes everything more complicated. And it's still user space. So it's not that much better and it's more work to do. Next. What we want to do is doing multicast forwarding in kernel space. It's a matter of performance, especially if we have not that much hardware. Lifting up everything into user space is really not that great. We would like to do it with like Unicast traffic, just let the kernel do its stuff. Next. And yes, IP multicast routing, it has been part of Linux forever. It works, it's fast, it's integrated, it plays nice, but it doesn't work for our use case. It has been done for multicast routing between Ethernet segments, and so it's not the solution we are normally looking for. Next. So, is it? Has someone looked into the Linux multicast routing and the new shiny stuff we got over the last decade or something like this? I must admit, I've looked into it not for years, and then last week I started looking into it again. So next, what's trouble? There are 4 points that making multicast difficult for us: retransmission on the same interface, selective forwarding, local traffic, and suppressing duplicates. Next. So retransmission on the same interface. I tested this a week ago. It seems to work. I don't know when they changed the kernel code, but I used a static multicast forwarding daemon, and I could send out multicast traffic kernel-based on the same interface again. Earlier kernel versions, years ago, just said, no, that's not allowed. So it seems at least this problem was solved a long time ago. I don't know how many years ago. Good, one thing done. Next. Selective forwarding multicast, one back. So yeah, sometimes we don't want to, we want to deal with incoming multicast differently depending on what was the last node who sent us. So to improve the efficiency of the forwarding a little bit, we could do this in theory with some clever dynamic firewalling. We might need access to something like the Ethernet MAC address, and nobody likes to dynamically load IP tables, EB tables, NF tables rules all the times, but it could be possible. Next. Local traffic. As said in the last presentation, you don't always have a nice router with a host attached, but kernel multicast forwarding only deals in interface-to-interface forwarding. It does ignore local traffic completely. The idea is that the local application should know which interface to use, which is bad if you have multiple radio interfaces. So, but we could change this today. There's something called virtual Ethernet devices. So it's just like a pair of interfaces. You put in all local traffic into one end, and it comes out of a real interface. So you move the problem from local traffic to interface. Hey, that's easy. Done. Next. Suppressing duplicates. Yeah. Because of radio transmissions and this non-transitivity, we often get the same packet multiple times because it's transmitted from multiple neighbors, and we need to filter this out. So we need custom code in the kernel, and nobody likes to write or even maintain a Linux kernel module. This is hard work, really hard work. Yeah, so what can we do? Next. Wait a moment, what was about new toys? There's something called Ebpf for a number of years. Extended or enhanced Berkeley packet filters. It's some kind of virtual machine in the Linux kernel. You can push, for some functions, you can push code into the kernel and do some custom stuff without writing kernel module. And there's XDP, Express Data Path. We don't need the Express path, but XDP can be attached to interfaces and do some logic based on an Ebpf program. For example, deciding to drop packets that are incoming, or maybe modify them, or redirect them to a different interface. That sounds interesting. So I got an idea. I have to admit, I could not test this in time, but maybe we have something to talk about. Next. So what I would like to do is combine all these things. We have a little Ethernet in the middle, so this resolves the local traffic part. We have at the end of the virtual Ethernet a firewall to make sure what's going on with traffic before we forward it. We use normal IP multicast routing on the outside to go to an outgoing MANET interface. And we can use the Ebpf filter to filter incoming MANET traffic, and then if we want, either redirect it to the virtual Ethernet pair for forwarding, or redirect it there and just modify the TTL field to make sure it's not forwarded but comes out of the same interface, or just drop it based on custom code. Next slide. So what's the good thing here? We have the Ethernet header available, so not a problem with IP tables that we don't know who sent us the multicast at the last hop. We can change the TTL field on the fly and recompute the checksum or with a helper function to make sure that that this packet will be handled locally but not forwarded. I've seen implementations of hash functions in Ebpf, at least for recent kernels, which improved what we can do with Ebpf. So in theory, we could do the complete SMF duplicate detection, either on sequence numbers or on hashes, there in the kernel. So this could be a way to completely do the whole forwarding chain inside the Linux kernel without writing new kernel code. Because from my point of view, writing a new kernel module just for MANET, I don't think this is feasible. Well, most likely the module will either be not accepted or will age badly. So that's it. Next slide is just questions. So what do you think?
Thank you. David?
David Lamputter. Two things. So first, there is specific reasons the Linux kernel multicast routing API is not suited for MANET, because it's designed to deal with consistent broadcast domains. So it was never intended to deal with cases where you have a disjoint network like this. And the fact that you can now use it for a money because the IIF equals OIF restriction was removed doesn't make it a good tool. That restriction was there for a purpose in the beginning, because if you have actual broadcast domains, the only thing that will ever achieve is create loops. I'm missing considerations here. What else will break by transferring this tool that was designed for broadcast networks to this new scenario that it very much was not designed for? That's the one thing. The other thing that we kind of skipped over in the sequence of discussion here is duplicate detection may sound necessary, but it is, in my opinion, fundamentally never the correct thing to do. So not only will you run into scaling problems as soon as you get a larger amount of multicast traffic, there's also the fact that there's a reasonable number of protocols which will send the same multicast packet multiple times at some intervals, which is just part of normal operation for those protocols. And if whatever you set up for duplicate detection doesn't allow that traffic to go through, then you're breaking the upper layer protocol. It becomes a question of timers relative to each other. If your duplicate detection is faster, in quotation marks, than the protocol using it, then it works. But that's, IP forwarding is not supposed to remove duplicates in general, and this also applies to multicast routing. I very strongly would argue that the solution should not, cannot, must not contain duplicate elimination. And I think that's it for now. I have more comments later. So
yeah, I would agree to most what you said, but that's the toolbox we have at the moment, and we would like to do multicast in our typically confusing radio environments with micro radios. So, and I don't think we really break less things by doing raw sockets. So this is just an idea, an option to see what we can do.
Yeah, we have more tools coming up, I think.
Okay, Julius?
So Henning, I absolutely loved your talk until slide 16. And then I was a little bit, well, the point is that so you're saying we don't want custom code in the kernel, which I agree with. And then you say, let's put Ebpf custom code in the kernel. There's still custom code in the kernel. Our problem here is that there is too strong a couple between the control plane and the data plane. We don't have a good API for multicast over mesh networks that will serve all control planes independently of the routing protocol. Now, the kernel is not immutable. If we have a good idea, if we know what we want the kernel to do, and if that is something that does not depend on the routing protocol, it can get into the kernel. It will no longer be custom code, it will be general code. And our problem here is that we currently, I mean, David hinted to the opposite of what I'm going to say, but our problem is that we don't have a good idea of what it is that we want, what general forwarding the kernel needs to do for our needs.
Yep. Yes, it would be nice to have some better user plane in the kernel. I definitely agree, but I worry that depending on what kind of network we are talking about, we need different solutions. We will need, for example, if we have a high data rate Wi-Fi network, we might deploy something very differently than when we have a VHF UHF network that has two different interfaces with 2 orders of magnitude different capabilities. So at the moment, we don't really know that well what we need, which will make it difficult to go to propose a new kernel module, write it, and get it accepted, because maybe a few years later we say, oh, we need something else again.
I think that indicates that we don't fully understand the problem. The notion that we need different algorithms for different networks indicate we don't understand the problem well yet.
Yes.
Donald.
Donald Eastlake, FutureWay Technologies. Just a real quick thing that obviously duplicate detection can't just be based on the packet, but has to be based on where it entered the mesh and a sequence number applied at that point, so that you can, sometimes you're supposed to have 2 packets that are binarily identical.
Can I quickly say that SMF adds an extension header, an IPv6 extension header, to make the packet unique?
So I think this is Lou Berger. My comment is to this presentation, but maybe also to Ronald's. I think it'd be really helpful to talk about how not only end hosts fit into the solution being discussed, but also routers, and how you fit into a wider routed network. And looking at, I'm coming at this from like the raw perspective, and in there, the wireless network is just part of a larger network. And one of the things I've been grappling with is how do you integrate all your routing information and make it so that the unique properties of your MANET are like constrained to the MANET, but you can also pass through your transit routes. And in this discussion, in this presentation, and I'm willing to bet in the future ones, although it would be interesting to hear in the future ones, really interested in how you fit into a routed network as opposed to just the routed MANET that connects hosts. Thanks. And if you want to talk about that for what you've presented, that'd be useful also. Thank you.
Yes, but that adds a whole other dimension and makes it extra complicated. So maybe. Henning?
Yes, I would say the transit routes always for Unicast and for Multicast get things more complicated, and we don't even know how to deal within the radio domain with the Multicast. We should not forget external networks, both just attached networks and transit, but if we don't have a good data plane to experiment with, then we have trouble even finding out what we need. So I don't say this is the final solution, but this might be a good way to experiment with things and maybe give us a few hints what we could work on for more general data plane.
Rick?
Rick Taylor. Thanks for the presentation, Henning. I do like your research. It's very interesting. A big fan of Ebpf and the cool stuff you can do with the Linux kernel. It's just a small question I have is, it's great that these are tips and tricks that can help us build a data plane in order to prototype and work out some of the protocols. I actually kind of think here in MANET, we have the bandwidth really to look at what those protocols should be. Following on from Lou's comment, I need a multicast domain that spans some of my fixed infrastructure that may be not just that one laptop connected to the router connected to the radio, but that may actually be a small sub-area network. There will be backhaul into the fixed infrastructure, that heterogeneous network of which some segment is one or more radio systems, going back to Ronald's original diagram earlier on, I think is probably more relevant for the working group than how do we beat Linux into submission. Don't get me wrong, it's great stuff, but I just want to pull it back to a bit more of an IETF focus. Sorry, talking about duplicate packet, I fundamentally believe radio systems are getting smarter and smarter and smarter, and a lot of them are running some kind of embedded real-time operating system anyway. They understand what's happening at layer 1 and layer 2. They are doing a lot of duplicate packet elimination anyway, based on information they have from the radio subsystem. And I think the naive approach of not deduplicating is actually the correct way to go. So I say naive, but it's actually the right thing to be doing. If the lower layer says, I've got 2 packets that are, as far as you're concerned, are identical, what is the IP layer to do? The IP layer should just forward those. It's not the IP layer's business to do that deduplication. And we've got to be really careful about that layer separation.
I don't think layer 2 can help us there, just as a personal comment, because you can push everything we do down to layer 2, of course. Then someone else needs to solve the problem. But that's not always helpful, especially with multiple radios. So,
my quick response, and then I'm going to shut up and sit down. This has always been the problem with the MANET working group. We live within the IETF. We're supposed to be layer 3 IP focused, but MANET problems often exist at layer 2 as well. And I'm really interested in what Donald's going to tell us about what's happening in 802.11, because for the link layer, really, that shouldn't be in the scope, but we all try and solve these MANET problems as a general thing.
Thanks, Henning. Thanks, commenters. Donald.
Hi, maybe I'll hold it. Hi there, I'm Donald Eastlake with Futureway Technologies. I was actually chair of the 802.11 mesh task group for the first half of its existence. Next slide. So, I'll try to go through these. First slides are pretty quick. You can read them at your leisure, but basically 802.11 is a very complex standard. Got all kinds of stuff in it. Get your own copy, read all 4,000 pages if you feel like it. It's very widely deployed. It's got all kinds of things you probably never heard of, and operates in all kinds of different spectrums and different control paradigms and stuff like that. Huge number of chipsets per year, so it's worth doing the effort to make improvements in them, because the cost of the engineering gets spread over a large number. Security is built into the hardware, so it's free to use, and you have to get the keying right. The working group is a link at the bottom. Next slide, please. It's got fragmentation and aggregation, multiple levels of aggregation, and mostly talk about the infrastructure mode and mesh. Next slide, please. Now I'm going to skip some of this. So this is what a data frame looks like in 802.11. 802.11 believes in a complex header with extensions rather than layering. It's all layer 2 in a sense, but you could still imagine ways of doing this with nested stuff. Over there on the right, the next to the last thing, is there's actually some data. There's a frame body. I don't know. And then there's the frame checksum. But there's space for lots of addresses, and these are all 48-bit MAC addresses. And the left end is the frame control, and the bottom shows frame control. They all have a version type and subtype, but what the remaining bits are depends. There's data type, data frames, and control frames, and management frames, and action frames, and multi-hop management frames, and on and on and on. Matter of fact, ran out of types and subtypes. So there are things with protocol version 0.1, not because it's really a new protocol, because they ran out of types and subtypes. Next frame, next slide. So this is the classic infrastructure ESS. You got a, it's just called the distribution system in the standard. It's very vaguely described so that you can instantiate it in many different ways. Access points, stations associated with that. Extended service set is this whole thing where the stations can all talk to each other as if they were local to each other within the same SSID. Next slide. So the APs beacon periodically. It could be any time, but actually it's always 100 milliseconds for normal cases. That includes their capabilities and SSID. And the stations associated with the access point negotiate pairwise keying, and the access point pushes down a group key. So the access point can send multicast or broadcast, and all the associated stations will be able to receive it. There are these 4 logical addresses: the real source, original source, final destination, and the actual transmitter and receiver's address. And I'll skip over the Unicast case, but for multicast at the bottom there, if it's the multicast source is actually the AP itself is sending it or behind the AP, then the AP can just multicast it because it can set the receiver address to be the same as the multicast destination address, and all the stations will happily listen to that. If you send them multicast from a individual station, it gets unicast to the access point, which then, so it has in it the multicast destination, but it uses the access point's receiver address, and then it gets multicast by the access point down to the stations. And that means the station does get the multicast that it sent back to itself. It receives it again, but it can tell because it has its own address as the source address in that frame. So it doesn't have any problem because even though this is in some sense a violation of the Ethernet axiom that when you send a packet, a frame, you never get it back. But as long as you can tell when you drop it, it's easy enough. Next slide, please. So how does it get reliability? Unicast stuff, it usually uses link level acknowledgement and retransmission. But of course, things go wrong, acts are lost, you might retransmit when you didn't need to, and so on and so forth. So there's a sequence number, and when it's fragmented, there's a fragment number as well. So you can always tell if you got something more than once. And of course, 802.11 is you're talking a single hop, and there's a goal is a maximum distance of 100 meters and stuff. The timing is sort of constrained, so you can figure out a reasonable number range and stuff. For multicast, there's got all kinds of things in there. People frequently complain about the unreliability of multicast in 802.11, but really anything you can think of as a reasonable way to make multicast more reliable has probably already been put into the standard. Now, whether it's implemented and widely deployed is a whole nother question. But sometimes people say, well, multicast is always sent at the lowest possible rate. That's not true. You can tell the access point whatever rate you want to send it at. If it's discovery, you might want to send it at a pretty low rate. But it's for data, you could send it at just what rate you think is necessary for the most remote station or something like that. You can have unsolicited retransmissions where these thing gets transmitted multiple times, and you just depend on the duplicate detection, and that more likely to get through. You can go through and poll every station to see if it received that multicast frame. Of course, this uses up a lot of airtime and kind of loses a lot of the advantage of multicast. But of course, there's a feature where you can send a bunch of multicast frames and then poll the stations for a block of acknowledgements and see which stations missed what. And because the receiver address and the destination address are separate, you could go through and serially unicast, which also eliminates, of course, a lot of the advantage of multicast and is useless if you're trying to do discovery. Next slide. There's also this ad hoc mode, which I think is mostly used these days for tethering. Like if you tether to an iPhone or something, it uses ad hoc mode. And that way all the stations beacon, and they just send directly to each other. And in some weird mode, you might think of it as a one-hop mesh. And in that case, you really sort of only need 2 addresses, because in every case, the source address and the transmitter address are the same, and the receiver address and the destination address are the same. But the header still has 3 fields, and the third field is this basic service set ID, which is how the ad hoc network kind of is identified. And of course, it may not be full connectivity. It's not very reliable. But if you want to send multicast, it's easy. You just send multicast, and everybody can hear you gets it. And those that happen not to be able to hear you don't. Next slide. So there is this fourth address in the header, which is optional. So why is that there? There's been various proprietary uses. Currently there are sort of two standardized uses. One is the general link feature, and the other is mesh. So general link basically has the idea you're sending something through a station across an 802.11 link through another station. And so the source, transmitter, receiver, and destination address are all separate, and they could all be there. It would all typically be different. So if you go back one slide for just a sec, you can in fact, in the standard, you can do this ad hoc thing, and you can make all those radio links be general links. And if you did that, there could be arbitrary networks behind each of these stations. Of course, the connectivity in the middle would still have this flaky one-hop pseudo mesh thing. So, but if you could do that. Of course, the alternative is to make these have a network behind the station, but make it still appear to be one station by putting a NAT in there or something. But anyway, go forward 2 slides, please. Anyway, you can also use general link in the infrastructure case, in which case you have an access point and associated stations, and you could have a network behind the station. Anyway, so the initial idea for mesh was it was just going to be used for wireless backhaul. People like to limit the charter scope initially. So all the mesh points, mesh stations would be access points. Might not actually have any stations associated with them. So it's somewhat of a pointless restriction, but it might look something like this, where some access points can only get back to the distribution system through other access points. Next slide. But fairly soon the mesh idea got generalized, and people decided it really should be look like more of a distant. It looks like a link from the outside. So the idea here is this packet, a frame actually, goes through the mesh along the solid line, and the dotted lines are other radio pairings between mesh stations. Next slide. So in mesh, all the stations send beacons periodically, and they include in that their mesh profile, which is a mesh ID. It's like the SSID, but different. They also indicate what protocol, what path selection protocol, otherwise known as routing protocol, they're using, the path metric, cipher suites, et cetera, et cetera. And they peer. It's an equal peering of equals between them, and negotiate pairwise keying. And then each station distributes to its peers the group key that it uses if it wants to transmit multicast or broadcast. And from the outside world, the whole mesh just looks like a layer 2 link. So you generally have 6 addresses: the original source, the final destination, the mesh source, which is where the frame entered the mesh, or where it originated if it starts inside the mesh destination, which is where it exits the mesh or terminates in the mesh, and then the actual transmitter and receiver on the particular hop. Next slide. So here's a connection from a station on an Ethernet LAN on the left to a mesh station that has this. There's a component called a gate, which you need to get out of the mesh. And then there's mesh links, and over on the right, we have a co-located mesh station, an access point, and a station that's associated with that access point. The station at the far right has no idea there's any mesh involved. It's just associated to that access point. So a frame in the middle would have all 6 addresses, which are the 6 addresses shown across the top there. Next slide. So this is just a table of all these addresses exist or don't exist for unicast and multicast, for frames that are transmitted internal to the mesh, as opposed to frames that start outside, transit, and leave the mesh. Next slide. So where these extra addresses go? Well, as I say, 802.11 has this complex header with an optional extension. So it is this mesh extension. It's got mesh flags, has a TTL 4-byte sequence number, and can have 0, 1, or 2 additional addresses, because in certain cases where the destination is multicast, you don't need additional addresses. So the source address and the sequence number as a pair is cached at the mesh nodes and used for duplicate detection. And there's nothing very definitive in the 802.11 mesh standard about how long it needs to be cached for, or things like that. So Unicast is this routing is determined by this path selection protocol, and the mandatory to implement one has both reactive AODV-like features, and it also has a proactive part which builds a tree from configured routes. So you can always use that tree, but you may get more efficient paths with the hybrid, with the reactive mode. Next slide. So multicast. So they're sent with the destination address, the multicast address. So you don't need separate receiver addresses for the physical receivers. Or alternatively, you can serially unicast by specifying individual receivers to get acknowledgements and retransmissions on each hop. So the receiver discards them if the TTL is counted down, obviously, or if they're duplicates, or if they're not from a peer. So it basically just floods it with duplicate elimination. And that gets your multicast or broadcast frame to all the nodes in all the mesh stations in your mesh. And this has always been in there. 802.11 has always had multicast that worked in this fashion since it's been standardized, 802.11s. Next slide. This is my last slide. So the question, well, okay, this is all at layer 2, and it's all like that, and you can have these gates that connect to the outside world, and this duplicate elimination may solve things inside the mesh, and the TTL is a sort of extra backup, so you can't really have looping and stuff like that inside the mesh that would be problematic. But what about loops in the external networks? But since everything is layer 2, it just uses a spanning tree and disables gateways and such that you don't have loops by the typical spanning tree method. So I think the flooding and duplicate elimination has got obviously some bad aspects and sort of a burden in storage of the nodes and so forth, but it's a pretty general and powerful technique for getting multicast to actually work in meshes and things like that. That's my last slide.
Thank you, Donald. Perfect timing. Questions?
Can you go back to the last slide?
Sure, back up one.
Can you clarify if this is one spanning tree for all traffic or one spanning tree for each source, like rooted at that source?
It's for all traffic, I believe. But it has been quite a few years since I was involved with this. And anyway, hopefully there weren't too many errors in this. I don't know.
Henning?
I have worked a little bit with 802.11s, and in my opinion, it was not working well in anything beyond a couple of nodes. But even then, because this AODV with proactive beaconing didn't scale well, 802.11s might be the best mode to use Wi-Fi if you want to do layer 3 routing over it, because you can just switch off the mesh protocol below it, and then you have a fully bridgeable single hop Wi-Fi ad hoc mode, because the original ad hoc mode doesn't work well on newer Wi-Fi versions. So even if we want to use a different protocol, 802.11s might be the single hop link layer we want to look into, because everything else on Wi-Fi doesn't work that well for MANET.
I would like to say that I am not supporting the current path selection protocol in 802.11s. Originally, there were going to be 2 of them. One got dropped at the last minute, and I think there could be better alternatives for the routing inside 802.11 mesh.
Julius?
Could you please go one slide back, slide 16, please? So here you're saying that you can do a conversion of multicast to unicast, right?
Right.
Does that mean that every node knows the membership of every multicast group, or does that mean that you're spamming the whole mesh with your multicast?
You're spamming the whole mesh.
Okay, thank you.
Yeah, by the way, so you don't just send general multicast frames for the purpose of discovery in 802.11 mesh. Discovery happens because the stations send beacons and then they peer. So when you're actually sending data, it never worries about getting them to anything but a peer that it already knows about. So you can just serially, you have that list of peers and you can serially unicast to them quite easily.
Do we have time?
And actually,
Sure.
if they're not a peer and you multicast or just some other random receiver that receives it, they won't be able to decode it anyway because they won't have the group key for the sender.
Sure, that's clear. Thank you.
Okay, thank you. We need to move on. Dominic, we saw you were briefly in the queue, but no, I was going to ask you to hold your question until the discussion.
Okay.
Next up is Sandy.
Hello? Hello? Do you hear me again? Hello?
Better before. I think you're a bit too loud.
Too loud? I'm not very sure. There's something wrong. Is it
Can you
better
hold-
now?
Yeah. Can you have the microphone at a greater distance from your mouth?
I use headset here, but I'm not very sure. There may be something wrong here. But now, if you hear me well, hello.
It's better. Yeah.
Yeah, it's better if you talk a little lower. It's pretty high gain, I guess. So if you can talk a little a little
Oh.
quieter, we can hear you better.
Okay. 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 Is it better now? Hello.
Yep.
Yeah. Go ahead.
Hello. Okay. Okay. Hello everyone. I'm Sandy Zhang from ZTE. This presentation is for beer in Babel. We have co-author Tony from Juniper. Next, please. At first, let's see what's beer. Beer is the acronym of Beer Index Explicit Replication. Beer is a new multicast technology. It can achieve multicast forwarding without explicit multicast distribution trees building, and it doesn't require intermediate nodes to maintain any per-flow state. Beer introduces a layer architecture to decouple the multicast packet and the multicast transportation. The multicast forwarding in Beer doesn't depend on the IP header, which has the multicast destination. It depends on the new Beer header. Beer forwarding is based on bit string in the Beer header that follows a layer 2 or a tunnel header, for example, MPLS, IPv6, or any tunnel, whose encapsulation header can indicate that Beer header follows. Each bit in the bit string indicates an edge router that needs to receive the traffic. The Beer architecture is defined in IETF 8279, and the Beer header is defined in IETF 8296 and draft Beer in 6. Next, please. There is the Beer layered architecture. The multicast forwarding is decoupled from the multicast packet. The multicast packet, which has the IPv4 or IPv6 multicast destination address, is recognized in the ingress router and the egress routers. The intermediate nodes forward the packet depend on the Beer header only. The multicast destination address of the packet doesn't be seen in the intermediate nodes. The control of the multicast packet among the ingress and egress routers is called multicast flow overlay. The ingress router encapsulates the multicast packet with Beer header and the necessary outer encapsulation, for example, MPLS, Ethernet, or IPv6. The egress router removes the Beer header and associated outer encapsulation, forwards the multicast packet to receiver or the next hop router. The Beer layer is the core part of Beer. The node forwards the packet according to the Beer header only. The outer encapsulation, as we mentioned, can be changed by each node. That means hop by hop. There is no multicast trees in the beer domain. The details of beer forwarding and beer header is described in the FC we mentioned above. The routing underlay is extending the routing protocols to build beer layer. The forwarding table used in beer layer is generated by the routing underlay protocols, such as ISIS, OSPF, or BGP, and of course Babel. And the underlay protocol is extended to advertise the node's beer information and compute the specific beer forwarding table. That means BIFT. Next, please. From above, we know that when we use beer, there is no multicast tree signaling and the multicast state in the network. Beer can work with any routing protocol to signal beer information used for BIFT calculation. For example, SIS, OSPF, BGP, and Babel, and the other routing protocol can do it as well. Beer can work with any L2 or tunnel encapsulations, as we mentioned, MPLS, IPv6, and so on. If the multicast traffic rate is not high, beer forwarding can also be achieved by software. So beer is perfect for Babel networks. Next, please. Let's see the beer signaling in Babel protocol. Babel route advertisements for beer router loopback addresses carry TLVs for beer information used for BIFT calculation. Beer traffic can be tunneled over beer-incapable nodes by any kind of tunnels. Because Babel is a distance vector protocol like BGP, methods used in beer BGP signaling can also be used here for Babel. This part will be added in next version. Next, please. For your information, there is an open source implementation for beer signaling in Babel protocol in the GitHub. That's all. Appreciate for your listening. Comments welcomed.
Thank you. Questions, comments?
Jeffrey from Juniper. I just want to add that the beer can achieve efficient multicast replication without building a tree. That's why it is the best multicast protocol I have seen. There is one case in other scenarios where it requires it uses a new encapsulation, a new forwarding algorithm. So when you need to use hardware-based forwarding, then you either need new ASICs or programmable chips. And that has been hindering its deployment to some extent. There's a chicken and egg problem there. But in the Babel environment, especially when the data rate is not high, you can use software-based forwarding. And as Sandy mentioned, that is one thing that makes it very attractive there. And so I just also emphasize the fact that it's efficient replication that does not flood the traffic, and yet you do not need to build trees. That's the key concept of it.
Julius?
Yeah, just two quick comments. So I don't have an opinion yet of whether beer is a good or a bad idea. I sincerely don't know. But what I am ready to claim is that beer does not suffer from the duplicate problem. Okay, so beer does not need duplicate detection. And as far as I can tell, just by reading the specs, I haven't checked that formally. As far as I can tell, it does not suffer from the problems that Ronald described in his talk at the beginning. Okay, and I think that at least, I don't know whether beer as a protocol is suitable for MANET, but the ideas behind beer is something that definitely we should be looking at.
David?
David Lampeter. This is going to be a bit of a longer, comment / additional notes. I first would like to point out a few things about Babel's functioning as it would apply to MANET. It's important to understand that when we have a situation where a mesh node is forwarding multicast traffic to multiple other mesh nodes, i.e., so it doesn't matter. So this is about the single hop behavior. So multiple mesh nodes in this case means that there's multiple paths for the traffic to progress. That traffic in current beer designs is always unicast. So you always have the replication into unicast on the single mesh hop level. Whether that is a good thing or a bad thing depends on the actual mesh properties. But you do only send it once. So if you have 1,000 receivers behind one mesh node, then it's only forwarded once to that mesh node. And this is not necessarily something about beer that needs to stay this way. It's only, so if you look at the problems with using multicast for labeled multicast propagation on lower levels in, for example, MLDP, the problem was always that you are moving from assigning labeling on control from the receiver to assigning that function to the sender of the multicast traffic, which has historically been learned to not work that well. However, in mesh networks, and especially if this ends up using the beer in IPv6 encoding, I believe this is a very solvable problem, which just needs a bunch of additions to beer. So this protocol, so in itself, beer will start out with only unicast packets on the lower layer. And if we want to use multicast capabilities of the radios, then that will be additional beer work, but it can be done. There is another thing I would like to point out. In a way, there's a commonality with 11S and even SMF to some degree, in that the reason that this doesn't need duplicate detection is because it's fundamentally an added layer of encapsulation. If you look at it sideways, kind of, then 11S is also an additional layer of encapsulation because you have this 6 address frame. And if you look at adding extension headers with sequence numbers, that's a very, very simple kind of added encapsulation, but still you're tacking additional data onto the packet. That is kind of the one important takeaway for me here. The way to avoid all the trying to deduplicate things is to add a layer, and that layer also tends to allow better routing behavior. And I think that's taken at this point, and we should focus on figuring out what the best encapsulation is, rather than trying to make it work without encapsulation.
I'd like to make a clarification. Beer IPv6 encapsulation, that means the draft adopted in Beer working group is Beer in 6. It's not encapsulated in Beer in IPv6 extension header. It's just a protocol follow IPv6 header. So we needn't to do the check of extension header for Beer in 6. We just read the IP protocol or next header field in the packet. We can know that there is a beer header followed. We need to do the extension header check.
Sorry, I was a bit unclear about that. That is what I meant. I did forget another thing. In the beer Babel work, there's one very important thing that is completely missing at this point, which is there needs to be some way to dynamically or within the mesh assign the actual identifiers for the beer nodes, i.e. the bit position. And that is the actual difficulty that doing beer in Manet will need to solve in some way.
Yes, only the edge routers need to be assigned bit position for it, and the intermediate nodes needn't to be assigned with the bit position. Yeah.
We need to speed up a bit. Henning, keep it short, please.
Quick. So we would just need deduplication for dense mode, flooders, multicast dense mode, not for sparse mode that follow a tree. If I understand this right, beer is just following a joined tree that is made out of the unicast roots and use the explicit bits to keep track which part of the already split traffic is still having to travel to multiple nodes.
Yes, only the topology is cared in the beer forwarding. We care not about the multicast flow, just the topology. That is the set of the egress routers. Yeah.
I don't know how to pronounce his name, but it's you.
Zhao Hui or Jeffrey from Juniper. I want to add one thing that I forgot to say earlier. It's related to the earlier point about income interface cannot be the same as outgoing interface in the traditional multicast forwarding. With beer, as David pointed out, is even on a LAN interface, it's neighbor-based. So we do not have this problem. You can receive traffic on an incoming LAN, and you can go out of the same LAN again to a different neighbor.
Lou?
Hi, Lou Berger. I'm new to beer, so I may have it wrong, but I think the really interesting point here is by adding, beer is adding a new forwarding layer or an additional forwarding layer, and that separates out sort of the IP semantics from the forwarding semantics, which I think is really good for solving the router-to-router problem that I asked about before. So I think David talked about the question for the group is what encapsulation mechanism should be thinking about. I want to generalize that to say what layering mechanism we should think about.
Thanks. We now move on to Pascal's presentation about multicast in roll.
This is also 15 minutes.
Hello, can you hear me okay? I don't know.
Hello, Pascal, we can hear you.
Cool. Did you give me the end, or will you move the slides?
You can give me control.
How do I do that?
Start talking, we'll figure it out.
Well, if you transfer it to me, then I will move them. Well, we can start already. So REPL is a role is the working group that defines the REPL routing protocol, and REPL is a distance vector that's optimized for a mesh that is using one or several routes to reach the outside. So most of the traffic is supposed to be from that route or to that route. And this is designed to operate in a constrained network, low power lossy network. So we did extensive optimizations to limit the knowledge of topology and routes and address that you need to have inside the network. And for that, basically what we are doing is we are routing mostly from the perspective of the route. So think about a distance vector, but instead of doing any to any, you will do route to any. And for that, the first thing that happens is you build a tree, which is not really a tree, it's a directed acyclic graph that is rooted at the root, and that basically points that the destination of that geodag is the root. So that gives you a loopless path for any node for the default routing. If you just want to do collection, that's enough, and you're done. If you want to be able to route down this DODAG towards the devices, then you will have to establish downwards path. And for that, you have two modes. One is what we call storing mode, and the other one is non-storing mode. So in non-storing mode, basically each node advertises its potential parents. So since it's a DODAG, it's not just one parent, it's multiple parents. So advertise its parents to the root. So each node says, I'm here, and my potential parents are those guys. And with this, the root is capable of rebuilding the whole structure of the DODAG in memory, and then use that for source routing. So that's the non-storing mode. In storing mode, you will use this DODAG and basically tell your potential parents about your addresses. And recursively, the potential parents will tell their own addresses plus all their children to the grandparents, etc. So you end up knowing every route downwards and using only the default route upwards. So that's the very basic of REPL. So it is anisotropic. It has a sense of up and down, which was inherited by Rift, basically to extend the model to multiple routes. And basically the top of fabric in Rift is like a route, but you have many of them. What else? We have extended REPL for an AODV model and for a centralized routing model. So a lot of what you've seen in Donald's slides, the tree that's possibility, or IODV that's a possibility, we have pretty much the same thing. So that's the basic of it, and we have different modes of operation and different instances. I need to talk about that a little. So if you basically want to make different optimization or build different DAGs, then REPL allows you to build multiple of those DODAGs. And each one that the node participates to will translate into a different verb. So we need to signal in the packet which verb, which routing table you're using, which corresponds to the REPL instance that installed that route. So we have a hop-by-hop option. So it's not the hop-by-hop routing here, but we have a hop-by-hop option in the packets to signal which REPL instance we are using. So it's an alternative like of source destination routing to go to a particular route. If you have multiple, if you're multi-homed, you can build one instance per exit point, and then you route along that instance and you will exit the expected place in the network. So the mode of operation one is non-storing mode. Mode operation 2 is storing mode. Mode of operation 3, mode 3 is storing mode with multicast. What it means is inside the DODAG, there is what we call the preferred parent tree, and we use that tree as the multicast tree, basically. So the leaves inject their multicast addresses as they would inject any cast address or unicast addresses. It's just that the parent, instead of keeping the freshest one, using what we call a path sequence, that's how we do mobility in REPL. Instead, we just keep them all and let the lifetime expire. And as we keep them all, then we basically unicast copy typically, but we could also broadcast copy a packet going down the tree to every child that's interested. So compared to what was said before, it's not a flood, right? We still register the multicast addresses. They are injected and aggregated as they go up the tree, as in traditional sparse. And the packets are then routed basically down that path. So you really have the two traditional modes where either you send a multicast packet all the way to the root, and then it will go down the tree, in which case you don't have to have this duplicate elimination prime. Or you can optimize and say, let me pass it to, when it's sourced anywhere in the tree, you can always pass it to everybody but the one who passed it to you, which is an optimization, but then you need to be able to not pass it back to the node that passed it to you in the first place. So the two models, the two forwarding models are available. If you don't want to have to care about where you received this packet or if you already received it, then basically, yes, you can leverage the tree and pass the packet to the root and let the packet go down down that tree. Next slide, please. Oh, no, it's me now. Yes, it's me.
You've got control.
Okay, so now that was the MapStream report. Now RAW has done another piece of work which is completely independent and completely that doesn't need any form of DODAG installed or anything. So you have a big crash and you need to flood some information, then Meeple can be your friend. So what it does, think again of a very large network with many nodes, and the problem that you want to, the thing you want to avoid is every node trying to relay this packet. So you basically want in an ad hoc fashion to create islands where one will send and the rest will receive. And when you're at the border of that island, then someone will send again and that will propagate that way. And so there is an algorithm which is tricore RFC 6206, which is used by Ripple anyway to cancel excessive flooding, and which is there leveraged as the base of the multicast operation. Basically what it does is, if there is an information that you want to synchronize on every node, a certain knowledge or a certain packet, someone sends it, and everyone runs a timer. And in a certain portion of the timer, you just listen. In the second portion of the timer, you have a random piece where you still listen and then you send. But you only send if you have not received more than a certain constant number of packets. So if enough packets of this same knowledge were transmitted around you, then basically you assume that everyone around you heard that packet and you don't need to resend. On the other hand, if you did not receive enough copies of this thing, then you will retransmit it. Now the efficiency is what it is, right? You have no guarantee that everyone will get it. It's a little bit problematic at the edge of the network. Because you might receive many copies from the inside of the network, and there might be sparse nodes beyond you on the edge of the network. And just because you received enough from one side doesn't mean that everybody on the other side got it. So there are a few corner cases with it. It's not quite efficient, but it's much better than flooding in a very dense radio environment. Next slide, please. Oops, it's still me, sorry. Okay, and then we've got extension work for Meeple, but I won't spend time on that one. The new work that we have started at 6LoWPAN, actually 6Low and RAW, is based on the fact that most of the time we don't use the storing mode, and so we don't have this tree. So we have also designed something which leverage the non-storing mode. In non-storing mode, there is a source route by the root. And so what we'll do in that case is we'll exploit the source route. Basically, the nodes use the extensions that we've made to IPv6 neighbor discovery to register unicast address. Now we are also enabling the registration of multicast address, which is maybe of interest for you guys, actually, because the first thing before you distribute traffic is to know who the listeners are. And MLD is a pool model that is not necessarily the one you want. You might want actually the devices to register the addresses that they listen to. And that's the model we use in IoT, because low power devices might not be listening to multicast queries from the MLD routers. So we want the devices to be able to sleep and tell their routers, hey, I'm interested in that multicast flow. If there is something that comes on that flow, well, you know, I want it. So when I wake up, I will come and see if you've got one. So basically the sleep proxy model. So the 6Low version is always to avoid having to do multicast and having the devices register the unicast and now anycast and multicast addresses they care about. And to make that work, now the root will do ingress replication. So basically, the root will tunnel to every edge router, and the edge routers will distribute over unicast or multicast layer 2 to the listeners. Since we talked about beer, I will speak a little bit more. We have two variations of the beer idea at the working group. Now, for the lack of interest, this work is pretty much stalled. Doesn't mean it's abandoned, but it means that we did not get strength and interest and consumers for those work, those pieces of work. So one is constraint cast, and constraint cast uses Bloom filters. So it's a bit like beer. I see it as beer family, but it's not exactly beer. And with the Bloom filter, what you can do is encode in a bitmap, not the bit of the destination or something like beer, but more a few bits, which basically represent the hash values for an address that you care about. So Blooms are used for finding if something is there, basically. And if you have a match, you're not sure it's there, but if you don't have a match, you're sure it's not there. What it does is for each address, for instance, that you have in a network, it will compute a 3-4 bit position using hash functions. And then to know everybody who's there, you basically OR all those bits. So now you've got the map of everybody who's here. Now, if you want to see if somebody is here, you hash his address, and you see if all the bits of this hash are present in the aggregate bitmap. If it is, then there's a chance the guy is not there. If it's not, then you're sure he is not there. So we can effectively leverage that for routing, and the way you could do it for deciding the source route path or to just find the destinations. Beer, classical beer, has bits for the destination. So the bit will say go that way. BRTE actually will signal bits for the hops. And so you can specify which route you're going to take by following the bits. The bits are not the destination, the bits are the hops. Ccast has Bloom for the hops. But it could have, I think it would have been more optimized to basically just Bloom filter the destinations. And so basically what you would do in your case, I don't think you're going to use this, but if you were to consider it, you would probably look at all the subscribers to your multicast and compute, have the bits for them. And when you have something to distribute, you basically distribute it to the aggregate Bloom filter of all those destinations. And when you want to forward, that's what is done in this draft. You just match the aggregate of your next stop to see if all the bits that you want to forward to are set, and if they are, then you forward to him. I'm not sure my explication was that great, but think about using Bloom filter as opposed to the just exact bits in beer. The advantage of that is that you're not limited drastically by the exact size of your bitmap. Like effectively, if you store more stuff in your Bloom filter than it's normal capacity, then you will have more false positives, but you will still route. You will just route down the graph a little bit too much, some copies, and then you realize that effectively some of the bits were coming from the left, some from the right, so the match does not exist further down. But that avoids this hard limitation of what size did you use for your bitmap? Oh, I have one more node, now I'm screwed.
We're almost out of time.
Okay, so I'm almost done. So the other thing we have is effectively beer for REPL. So then again, we have this tree, right, starting at the root. And so what we care about in REPL is compression, right? We don't want to have a lot of state and a lot of big advertisements. And what is very cool with beer, knowing that we have the same problem as everybody to assign bits, it's not solved, right? We have same question, the bits must be assigned, but say the bits are assigned. And we have, see it as a tree, even if it's a geodag. When instead of advertising your address and all the address of your children to your parent in storing mode, what you could do is send a single bitmap for you and your children with all the bits that represent you and your children's set. So basically, when you do that, the parent receives the bits for one child, for another child, for another child. What he will do is he will OR the different bitmaps that he got for all his children, and that ORed aggregate bitmap, that's what he will pass to his own parent. And as you go up the tree to the root, then at the end, all the bits should be set for every destination, and the root knows that this bit is via this particular children. So every node will keep the bitmap it got from its children, and now a packet that you want to forward, you will basically set the bits that you want to reach, and it will be ended with by each hop to all its children. And if one children matches, that means the one of the bits that you care for is effectively set, then you forward to that child. So the cool thing is, instead of maintaining in your database one entry for every descendant, for every IP address of every descendant down the tree, you just keep one bitmap for every direct child. And you forward along the bitmap. And that's pretty much it. That's all I had for you. So I guess I hope I have time.
Thank you. I really would want to go directly into the discussion part. Otherwise, we will have no time for Julius's presentation on the end. So if you have questions for Pascal specifically, please take them to the mailing list or mailing lists.
Yeah, so we have the general discussion part right now, and I've given 15 minutes for that, allowing 10 minutes for Julian's. Anybody? We got everything. If we got everything in, maybe we should go to Julian's presentation then. We've got about 20, just over 20 minutes left, 24. All right, why don't you bring up Julius's?
No.
What? Okay, go ahead.
Do you want to do Julius first and the discussion at the end, or?
Yeah.
Okay, that's fine.
We didn't have anybody jumping up for that. Oh, okay. Sorry, we had some online people. Well, let's do Julian's and then we'll do the discussion at the end. Okay.
As you wish. Okay, then I'll try.
Apologies for the confusion.
So, okay, while the slides are being put up, I'm Julius Krobacek, and so I had nothing interesting to say about Multicast, so I asked the chairs for the opportunity to show the Manet group what we have been doing recently in the Babel group. And well, it was worth trying. I was expecting the chairs to say, no, that's off topic. And to my great surprise, they said yes. So thank you very much to the chairs. Next, please.
Yeah, do you want control, by the way? Now that I know how to do it?
I'm fine. So most of you hopefully have heard about Babel. For those who haven't, Babel is a traditional routing protocol, which originally was designed for hybrid or heterogeneous networks. So I was seeing at the time people struggling with putting mesh networking protocols on networks that were mostly wired. So that had a wired backbone with some meshy bits at the edges. And that did not necessarily work very well when most of the network was traditional structured. And so I tried to design a protocol that is a traditional routing protocol but that happens to deal well with the meshes. Next, please. So Babel became an IETF standard track protocol in January 2021, about 2 years later than I expected. That will be familiar to everyone here, I think. And since then, we've done a number of useful extensions and a number of useless extensions that we've abandoned. And I would like to quickly mention 4 of them. They're authentication, source-specific routing, v4 via v6, and RTT-sensitive metrics. And I would like to point out that all of those have 2 independent implementations, that they interoperate to the extent possible with the base protocol. And the important point, we've been trying to design protocol agnostic extensions. They are implemented in Babel, but there is nothing in principle that would prevent them from being generalized to other protocols. And my goal here is to have people steal our ideas. Next, please. So MAC authentication, we've done a minimalistic and easy to implement authentication protocol. We have another authentication protocol for when you need more features. And what is original in this protocol is that it is provably invulnerable to replay. So most of the authentication protocols, if you look, for example, at Ebpf, they do not deal with replay in the general case and just rely on properties of the routing protocol so that replay attacks are not useful. And that makes reasoning about the security properties uselessly complicated. Here we are invulnerable to replay, and it was designed to be implementable on plastic home routers. It doesn't require real-time clocks, it doesn't require persistent storage, and it does not depend on features of the Babel protocol. It is completely general. Next, please. Source-specific routing, it's sometimes called ASDR for source address dependent routing, is an extension that allows routing packets depending on their source, and it allows a cheap form of network multi-homing. So you have your network, it's connected to 2 ISPs, and you want packets to be directed to one ISP or the other ISP depending on their source address. Or in other words, the source node controls which edge router is reached by setting the source address of the packet. It requires kernel support, but the kernel support is in since Linux 3.11. And for best performance, it requires host changes, but it does work without host changes. And again, it's something, so that's something that would be very easy to implement in something like OLS RB2. Next, please. Okay, that's the latest one, the one I'm currently excited about. It's v4 via v6. We call it v4 via v6 routing. And the goal of that is to allow routing IPv4 through IPv6 only nodes. So here on the right, you have a bunch of double stack nodes, and some of those nodes need to be sending IPv4 traffic. But in the middle of your network, your backbone consists of IPv6 only nodes. Well, v4 via v6 allows sending the v4 traffic through the v6 nodes, the goal being here to reduce the amount of administrative overhead. And there is no translation, there is no tunneling, there is no overhead. So usually I always try to work out what are the trade-offs. And in the case of v4 via v6, I cannot see any trade-offs. To me, it looks just like magic. So we've enabled it by default, expecting our user base to complain. It's been deployed for a couple of months. Nobody seems to be complaining. We've had some comments saying it's pretty cool to have more routes, but other than that, everything seems to work. It does require kernel changes. The kernel changes for IP were done in Linux 5.2, and Toki, Hale, and Jorgensen implemented the changes for ICMP in Linux 5.13, so the implementation will disable it if your kernel is too old. And again, that's something that's completely protocol agnostic. It has some very nice features and can be generalized to other routing protocols. Next, please. And finally, that's something that I'm feeling very ill at ease with. Ronald has been pushing me to push it forward. So it's an extension that's extremely useful. It allows computing automatically metrics by looking at routes RTTs, and at the same time, it does not suffer with major stability issues, which is if you do RTT naively. The problem is that I think that I'm very ill at ease with it. We've done a lot of experimentation. It works surprisingly well. And the problem is that we don't understand why it works. And so that makes writing down the draft very difficult. So the draft has been adopted, but it's been in a state in which I don't manage to finish it for a long time. It's widely deployed in production because it is extremely useful. And the fact that the draft is not ready yet didn't prevent a completely independent implementation, again by Toki, Hale, and Jorgensen in Bird. It is not quite protocol agnostic. It would need some significant tweaks to be made to work well in a protocol that has different dynamics from Babel. Next, please. Well, okay, so we have implementations of at least 4 useful extensions that are deployed in production and that are mostly protocol agnostic. You should consider stealing the ideas behind them for your favorite routing protocol. I promise we won't get offended. To the contrary, we'll take it as a compliment. Thank you for your attention.
Thank you, Julius. One quick question from Henning. Henning?
Sorry, forgot to activate the microphone. source-specific routing. Does it now work with version 4 in the kernel? I remember when I stole the idea years ago for my OLSR version 2, it was only version 6 in the kernel.
No, it's version 6 only, and the implementation that simulates it with policy routing has been removed from the implementation.
Okay.
Nobody, in order to do multi-homing, cheap multi-homing with IPv4, people just NAT. Okay, so nobody seemed to be interested, and we haven't pushed it because the users were not interested.
Yeah, version 4 destination with version 6 next hop, if I read your description correctly.
That's a different extension.
This yeah, so the
yeah, that's
the
what
other one.
that's what v4 via v6 does. That's correct.
Okay, good. That's it.
Thank you.
All right, so now we have the general discussion. So people that were online and in the queue, now's your time.
David Lamputter again. This actually a little bit ties into the Babel presentation, but also beer for multicast routing in Manets. The hardest problem that I see, which I've already noted, is assigning the identifiers for use in beer. And I would like to note two things about solving that. So either the mesh becomes its own beer domain, which is a perfectly fine thing to do, even if other parts of the network also use beer. There's no problem with having the edge of the mesh just be a transition between two different beer domains, which allows limiting the scope of the assignment of identifiers for beer to inside the mesh. But also, if the signaling mechanisms for this can be designed in a suitable protocol agnostic way, then there's no problem with having this work inside of Babel to assign identifiers inside of the mesh and then transition into ISIS or OSPF or BGP at the boundary of the mesh and just continue the same kind of signaling. Whether that's actually desirable and or whether people are actually going to implement it for BGP, ISIS, or OSPF is a different question. But both of those are fundamentally viable approaches.
Henning?
Yeah, we have talked quite a bit about that we need something in the forwarding plane. Bia talked about it because it needs some bits and must send it somewhere. I talked about this, and someone mentioned MPLS. Has someone experienced how well MPLS works in MANET environments? Because does Wi-Fi, do most Wi-Fi chips support it well? Because at least some of the more esoteric radios that like to do MANET thing tend to be a little bit conservative what they accept as over the layer 2.
Jeffrey here. My on-site tool does not allow me to raise my hand now. I couldn't find it, so I'll just try. MPLS, it's probably mentioned in the context of beer following MPLS header. However, beer does not require MPLS at all. It can work with MPLS. It can work with any layer 2 header or tunnel header. So you can use beer without MPLS at all. Now, also going back to the question of running beer in a MANET network itself, not at the IP layer. Originally, I was thinking it works very well, and then I realized that in a MANET network, I assume it's mostly a radio network, and quite often you want to reach multiple destinations over the same radio. And in that case, beer itself may not be a very good fit because beer forwarding is neighbor-based. You can only send it one by one. But if you don't consider that part, then the beer itself, the architecture, even though it currently is based on the IP layer, it's for the over IP routing on the layer, but the beer encapsulation and beer forwarding algorithm is actually not limited to IP to layer 3. You can do it at layer 2. All you need to do is map a layer 2 station to a bit in the bit string. Everything will still work well. That's very nice about it.
Julius?
Yeah, I'd like to come back to the point that David made earlier. So David made two points that I fully agree with. So he said that the protocols that work well for multicast are protocols that use extra encapsulation. And that basically the alternative to encapsulation is to have duplicate suppression. And if you have duplicate suppression, you're doing two things that are very evil. One is that you break protocols that resend the exact same packet. So there is one protocol that does that and that you're using all the time. That's DHCP-v4. So duplicate suppression needs to handle specially DHCP-v4, which is a horrible layer violation. And the other thing it does is that it puts potentially unbounded amounts of state in the forwarding plane. If I'm correct, that's essentially what MPL does. So it looks like we have two things, one which we definitely dislike, that's duplicate suppression. The other one, which is not very elegant, which is to encapsulate all of our packets as is done in beer, as it's done in 802.11s, and so on. And I'm wondering whether anyone, though I'm not expecting an answer now, but does anyone have any ideas? Is there a third possibility that allows to exclude both of those places? If we find a third possibility, then we could have a nice diagram with a triangle. We'd call it Lamperter's triangle, and David would be famous. So I'd like to encourage everyone to think about, is there a third possibility?
Okay, Lou, go ahead.
So a couple of comments. First on MPLS, MPLS is a data plane. It's also a control plane, or has lots of control plane protocols associated with it. From a data plane perspective, it has a nice property of being these stackable labels. So, maybe there's a way to use or abuse the data plane for the layering that we talked about earlier, but I wouldn't try to say that any of the MPLS control protocols are at all appropriate for MANETs. And I don't think anyone suggested that. I didn't hear that. And if someone suggested it, I would agree with the comment that it's not a good idea. So that's on MPLS. The other comment was actually in response to the prior, to the third leg of the triangle, to the Lamperter triangle, is one option is to leverage Ethernet header. And there's a lot of radios out there like Wi-Fi that have an Ethernet header, and maybe we can use and abuse the addressing that's going on there and allow for not carrying extra bits on the wire or not adding extra headers. So I'd like to just add that in as that third leg.
Turles.
I was already pointing out on the mailing list that we did have a lot more in-depth starting evaluation of using beer or beer-like technologies in role specifically, where the goal was not only to do multicast with it, but also as an actually more efficient way to steer the traffic hop by hop through the network, so that you don't have to have this expensive routing state in a role network. And I think the way I'm intonating that may already show you that there may be good differences to other use cases where you have more energy and where you love to have routing, and you would, for example, rather rely on them. So one of the technologies that we've done in the beer working group also, which is in North 48, is BRTE, and that is basically allowing you to hop by hop steer the packet through the network with for a steering solution, probably the most compact encoding, and that was exactly the BRTE thing was what we thought role would very much benefit from, as opposed to relying on hop by hop using the IGP routing information. Now, obviously, That requires you to have topology information on the router that sends it, so that you can calculate that path hop by hop there, like we've done it in MPLS networks with RSVPTE and EROs. So pretty much same thing, just very much more compact encoded. And that probably wouldn't be something you want to do with Babel, and unless you start disseminating topology information sufficiently well, like we do it in ISIS or OSPF. I would assume normally you don't have that information. So yeah, I'm rambling a lot of hopefully funny details, but I think it shows that the solution environment is a lot wider, and it shows also that the different worlds that we have here with Babel, Roll, and Manet may not necessarily need one and the same option out of all these multicast things that we have in the end.
Rick Zoner. Very quick comment about putting topology information out into Manets. The churn for most Manet use cases is so high that you just absorb all your bandwidth, keeping the topology consistent. So let's not drift off into that. Just a quick comment about duplication of packets or deduplication of packets. There are two reasons for having duplicate packets in your system. One is because it's meant to be there. DHCP-v4 is a classic example. You know, the application there is saying, actually, I need duplicate packets. The other reason is because your multicast system can't remove them or accidentally create them. And I think there needs to be a real separation of these two things. Generic deduplication of packets within a Manet is not something we want to pursue. SMF, due to the way it works, creates duplicates by accident and therefore must clean them up. Other systems may not create duplicates. I just want to make sure there's some clarity there before we get fixated on deduplication. And Lou's point about using the frames, using the lower layer frames for some sort of identity is a good plan.
But layer 2 dependent.
Yeah, I'm slightly confused that earlier, I think, David Lampotter again. But I have something other to, well, ask here. With beer being suggested in Roll already, I don't have the history on why that fizzled out or anything. If there's any... Oh, apparently it fizzled out due to the pandemic. If there's any actual technical reasons, we should totally dig them up and not repeat the same mistakes.
Thank you. So my takeaway is that beer is definitely something that we should look into for Manet, maybe also for Roll, where it was already on the to-do list. It's really something really important. I closed the queue because we're out of time actually. So, but do please continue this discussion on the mailing list and the mailing lists. I would say, I mean, people don't like cross posting, but to keep this crowd together, we cannot escape that. I think. For the moment. And Alvaro, any final words of wisdom from you?
Sure, Alvaro Thunder Routing AD. So yes, let's continue the discussion. I would hope that there are commonalities. We all understand that LLMs and mesh networks and Manet networks and all this stuff are different, and some have different needs. But what I would really love to see is some type of more sharing, right? Instead of going back and saying, oh, we learned about stuff, let's keep working in Roll or do Manet, whatever, something else, to try and keep the discussion going. Maybe that means we meet more often like this, because I think this was very productive. Maybe it means we on purpose think about any common building blocks that could be used for different things, and we work on that in some place. One of the working groups, one of the existing working groups, maybe we spin up a new effort, whatever it is, But if we can figure out those building blocks, then maybe we can make more progress than just going off and then coming back every other IETF to share what we did. And it's great for learning, but I would really like to, given the interest, that we take advantage of this and keep building on it. But thank you everyone for participating.
Thank you. Sounds like maybe an interim would be an idea, but I will discuss this with the other chairs. Thank you all for your contributions, and enjoy the rest of your IETF, and see you in London, hopefully. Any words from you?
Just thank you. Take your slides down.